Today we're doing section 7.1, diagonalization of symmetric matrices. A symmetric matrix is a matrix A such that A transpose equals A. Such a matrix is square. Its main diagonal entries are arbitrary, but its other entries occur in pairs on opposite sides of the main diagonal. Theorem 1. If A is symmetric, then any two eigenvectors from different eigenspaces are orthogonal. Theorem 2. An n by n matrix A is orthogonally diagonalizable if and only if A is a symmetric matrix. Let's look at example 1. Orthogonally diagonalize the matrix A, whose characteristic equation is shown. So the first thing we need to do is we need to find a basis for lambda equals 7 and a basis for lambda equals -2. So let's start with a basis for lambda equals 7. So we need to solve our characteristic equation A minus 7i equals 0. So that would give me -4, -2, 4, -2, -1, 2, 4, 2, -4. So when I go through, I can add row 1 to row 3 and cancel out row 3. Then I can take half of row 1 and divide it by 2 and add it, subtract it from row 2, and that row will also become all zeros. And then I just need to divide row 1 by -4. So x would be -1/2 x2 plus x3, and then x2, x3. This would be in terms of x2 and x3, and we would have -1/2, 1, 0, plus x3, which would be 1, 0, 1. So V1 is what we'll call it, is 1, 0, 1, and V2 is -1/2, 1, 0. So now we need to do the same for lambda equals -2. We need to find the basis for lambda equals -2. Okay, so we have this matrix, 5, -2, 4, -2, 8, 2, 4, 2, 5, equaling 0. So going through with this, I want you to go through and try to solve this one on your own, and then check your work with mine. So pause now. So the first thing that I did is I added row 1 to row 3 and row 3 to row 1 to get 9, 0, 9, 0. And then I added negative row 1 to row 3 to get zeros and divided row 1 by 9 and row 2 by 2. Then I added row 1 to row 2. And then I divided row 2 by 4. So V3 would be -1, -1, half 1. So that was the first step. So V1 and V2 are linearly independent but not orthogonal. So that's one thing that we know. So V1 and V2 are linearly independent but not orthogonal. And recall from 6.2, the projection of V2 onto V1 is as follows. So we know, so some notes that you might want to write down. V1 and V2 are linearly independent but not orthogonal. And recall from 6.2 that the projection of V2 onto V1 is as follows. V2 dot V1 all over V1 dot V1 times V1. And the component of V2 orthogonal to V1 we're going to call Z2. And now we can put these over them. So we're going to, the component of V2 orthogonal to V1 is going to be called Z2. And that's going to be V2 minus V1 dot V1, or dot V2, sorry. All over V1 dot V1 times V1 So that will equal V2 is negative 1/2, 1, 0, minus V1 dot V2 is negative 1/2 over V1 dot V1 is 2 times V1, and negative 1/2 over 2 is negative 1/4. And so when I subtract these, I get negative 1/4, 1, and then 1/4. So my set V1 and Z2 is an orthogonal set for eigenspace lambda equals 7. Z2 is a linear combination of V1 and V2, so it's in the eigenspace. So V1, Z2 is an orthogonal basis for the eigenspace lambda equals 7, and that's the basis theorem. In that sense, it's two-dimensional. So our next step is we need to normalize V1, Z2, and V3. So let's start with V1. So first, we find the length, which equals the square root of 2. We're going to call this U1, and that would be 1 over the square root of 2 times V1 Then we're going to normalize Z2. First find the length, and that would be negative 1/4 squared plus 1 squared plus 1/4 squared, which equals the square root of 18 over 4. So U2 would be 4 over the square root of 18 times negative 1/4, 1, 1/4. And I would get negative 1 over the square root of 18, 4 over the square root of 18, and 1 over the square root of 18. Then we need to normalize V3. So that would be negative 1 squared plus 1/2 squared plus 1 squared. That would be the square root of 9/4, which equals 3/2. So U3 would equal 2/3 times negative 1, 1/2, 1, which would be negative 2/3, 1/3, 2/3. And this should be negative here and negative here. That's a negative 1/2. I dropped it by mistake. So we normalized vectors V1, Z2, and V3. Next, from theorem 1, U3 is orthogonal to U2 and U1 and U2. Hence, U1, U2, and U3 is an orthogonal set. So some notes there. From theorem 1, U3 is orthogonal to U1 and U2. Hence, U1, U2, and U3 is an orthogonal set. So P is going to equal U1, U2, U3, which would be 1 over the square root of 2, 0, 1 over the square root of 2, negative 1 over the square root of 18, 4 over the square root of 18, 1 over the square root of 18, negative 2/3, negative 1/3, 2/3. D, from our eigenvalues, 7, 7, 2. And P orthogonally diagonalizes A. And A equals P D P inverse. And I wish you could see it all, but we can't. So that was quite a bit. So first we found the basis. And then we came up with our orthogonal set, normalized our vectors, and then orthogonally diagonalized the matrix. Theorem 3, the spectrum theorem for symmetric matrices. The set of eigenvalues of a matrix A is sometimes called the spectrum of A, and the following description of the eigenvalues is called the spectrum theorem. An n by n matrix A has the following properties. 1. A has n real eigenvalues, count in multiplicities. 2. The dimension of the eigenspace for each eigenvalue lambda equals the multiplicity of lambda as a root of the characteristic equation, and this was shown in example 1. The eigenspaces are mutually orthogonal in the sense that eigenvectors corresponding to different eigenvalues are orthogonal. And 4, A is orthogonally diagonalizable. Let's look at example 2. Construct a spectral decomposition of matrix A that has the orthogonal diagonalization. So here you need to keep in mind that A equals P D P inverse. We're going to denote columns P with U1 and U2. Okay, so here, what we need to do is we need to take A and solve 8 from here times U1 transpose plus 3 times U2 transpose. And that should give us A when we add them together. So what I'm first going to do is I'm going to find U1 transpose. So that's U1 times U transpose, U1 transpose. And that would give me 4/5, 2/5, 2/5, 1/5. Then I'm going to find U2 transpose. So U2 is -1 over the square root of 5 and 2 over the square root of 5 times -1 over the square root of 15, or 5. Sorry about that. 2 over the square root of 5, and that ends up being 1/5, -2/5, -2/5, 4/5. Now I need to find A, which is 8U1 transpose plus 3U2 transpose. So I'm going to take 8 times 4/5, 2/5, 2/5, 1/5, plus 3 times 1/5, -2/5, -2/5, 4/5. End up getting 32/5, 16/5, 16/5, 8/5, plus 3/5, -6/5, -6/5, 12/5. When I add these together, I should get 35 over 5, which is 7. 16 minus 6 is 10 over 5, which is 2. 16 minus 6, which is 10 over 5, which is 2. And 8 plus 12, which is 20 over 5, which is 4. And that gives me A.